Ever wondered why sand settles at the bottom of a glass of water, but milk particles don't? Welcome to the intriguing world of suspensions. These fascinating mixtures are everywhere, from the orange juice you enjoy at breakfast to the murky pond water you might have seen on a nature walk. Suspensions are a type of heterogeneous mixture characterized by solid particles being dispersed in a liquid or gas. But it's not as simple as it sounds. The particles in a suspension are more than just suspended. They're involved in a mesmerizing dance, guided by the laws of chemistry and physics. You see, it's the size of the particles, their charge, and even the temperature that determines whether they'll float, sink, or perform a stunning mid-liquid ballet. It's why sand, with its larger, heavier particles, sinks in water, while the tiny fat globules in milk stay suspended, giving it that creamy appearance we all love. But why should we care about these seemingly trivial everyday phenomena? Well, suspensions are not just scientific curiosities, they have significant implications in various fields, from the food and drink we consume, to the medicines we take, to the cosmetics we use, and even to the fuels that power our vehicles. Understanding suspensions allows us to manipulate their properties for our benefit. For instance, in the pharmaceutical industry, the design of drug suspensions can greatly affect their effectiveness. Similarly, in the food industry, the stability of a suspension can make the difference between a delectable smoothie and a lumpy, unappetizing mess. As we delve into this captivating world, we'll uncover the factors that influence a suspension's behavior. We'll explore rheology, the study of how matter flows. We'll look at the role of particle size and volume of sedimentation. We'll examine how particle charges and caking affect suspensions. And finally, we'll consider the impact of changes in solubility due to variations in particle size, polymorphic form, and temperature. So buckle up, fellow chemistry enthusiasts. As we dive deeper, you'll discover that suspensions are not just a simple mix, but a complex dance of particles. Have you ever noticed how ketchup behaves differently from water? That's rheology in action. The term rheology might sound like it's straight out of a science fiction novel, but it's actually a branch of physics that deals with the deformation and flow of matter. In the context of suspensions, rheology is critical because it helps us understand how these mixtures behave under different conditions. Imagine a jar of orange juice with pulp. When you shake it, the pulp tends to distribute evenly, but leave it still for a while, and the pulp settles at the bottom. This is all about rheology. Suspensions are a class of materials that include liquids or gases with tiny solid particles dispersed throughout. The behavior of these particles and how they interact with the surrounding medium is a key area of study in rheology. The rheological properties of suspensions can be influenced by several factors, such as the size and concentration of the particles, the nature of the dispersing medium, and the temperature. For instance, a suspension with a high concentration of particles tends to be more viscous or thicker compared to one with a lower concentration. One of the fascinating aspects of rheology is the concept of non-Newtonian fluids. Fluids that don't follow Sir Isaac Newton's law of viscosity. Remember our ketchup example? Ketchup is a non-Newtonian fluid. It becomes less viscous or thinner when you shake or squeeze the bottle, allowing it to flow more easily. Understanding rheology is crucial not just for making better ketchup, but in a wide range of applications, from improving the formulation of medicines and cosmetics to optimizing industrial processes. Rheology helps us predict the performance of suspensions, but there's more to the story. The size and volume of sedimentation, the charges on the particles, and even changes in solubility due to factors like temperature or the polymorphic form of the particles, all play a role in shaping the behavior of suspensions. So, let's delve deeper into these aspects in the following scenes. Why does the thickness of orange juice vary? It's all about particle size and sedimentation. In the fascinating realm of suspensions, particle size and sedimentation volume are key players. These two factors significantly influence the behavior and stability of suspensions. Let's break it down. Particle size is a crucial factor because it influences the rate at which particles settle in a suspension. If you've ever wondered why some particles in your orange juice settle at the bottom while others remain suspended, the answer is particle size. Larger particles tend to settle faster than smaller ones. This is due to the influence of gravity, which pulls larger particles down more quickly. In essence, the size of the particles determines how quickly a suspension will separate into its individual components. Now, let's turn our attention to sedimentation volume. Sedimentation volume refers to the volume occupied by the sediment once the particles have settled. In the case of our orange juice, the sedimentation volume would be the space occupied by the pulp at the bottom of the glass. A high sedimentation volume indicates a stable suspension as the particles are well dispersed and slow to settle. Conversely, a low sedimentation volume suggests that the particles are quickly settling out of the suspension, indicating instability. Together, particle size and sedimentation volume give us a snapshot of a suspension's stability. They allow us to predict how a suspension will behave over time and under different conditions. For example, if we know that a suspension contains large particles and has a low sedimentation volume, we can predict that it will quickly separate into its individual components. However, these are not the only factors at play. In the world of suspensions, everything is interconnected. The size of the particles and the volume of sedimentation can influence other characteristics, such as the viscosity and flow properties of the suspension. Particle size and sedimentation volume play a vital role, but the charge on particles is equally significant. Ever wondered why some powders clump together while others don't? It's all about particle charges and caking. Let's dive into the thrilling world of suspensions, where tiny particles hold the power to influence the stability and usability of an entire system. To illustrate this, we'll look at two key factors: particle charges and caking. First up, particle charges. These are electric charges that exist on the surface of particles in a suspension. These charges can be positive, negative, or neutral, and they play a significant role in the stability of the suspension. Here's how. Similar charges repel each other, so particles with the same charge will push away from each other. This repelling force can prevent particles from clumping together and settling out of the suspension, maintaining its uniformity. On the other hand, opposite charges attract. So, if particles with different charges come close, they'll stick together. This can lead to faster sedimentation, a process where particles settle at the bottom, causing a clear separation between the particles and the liquid. Now, let's talk about caking. In the context of suspensions, caking refers to the tendency of particles to stick together and form a solid mass, or a cake. This can happen due to a variety of reasons, such as moisture absorption, pressure, or temperature changes. And why is this important? Because caking can drastically affect the usability of a suspension. If the particles cake together, they can't be uniformly dispersed in the suspension, leading to inconsistent properties and performance. So you see, the little things matter. The charges on particles and their tendency to cake can make or break a suspension. They determine whether a suspension remains a homogeneous mix or ends up as a separated mess. While these factors are crucial, changes in solubility due to temperature and polymorphic form can't be ignored. But that's a topic for another time, so stay tuned as we continue to unravel the fascinating world of suspensions. Did you know the solubility of substances can change with temperature and polymorphic form? It's a fascinating fact and one that has significant consequences for the world of suspensions. When temperature fluctuates, the solubility of a substance in a suspension can either increase or decrease. This can dramatically alter the stability and behavior of the suspension itself. Now, let's talk about polymorphic form, Substances can exist in different forms, each with unique physical and chemical properties. Changes in polymorphic form can lead to alterations in solubility, which in turn influences the state and performance of the suspension. For instance, an active pharmaceutical ingredient may exhibit different solubility profiles in its different polymorphic forms. This could potentially impact the effectiveness of a drug suspension. Understanding these complex phenomena helps us harness the power of suspensions in various fields. From creating more efficient industrial processes to developing better medications, the implications are as broad as they are profound. From the orange juice you drink to the medicine you take, suspensions are everywhere. They're more than just mixtures. They're complex systems where the behavior of particles matter. Rheology, particle size, sedimentation volume, particle charges, caking. All these elements play crucial roles in making suspensions work. Understanding these factors provides valuable insight into how to improve and innovate the products we use daily. For instance, in the pharmaceutical industry, controlling the properties of suspensions can enhance the effectiveness of medicines, making them more beneficial for us. On the other hand, in the food and beverage industry, the right suspension properties can improve the texture and taste of your favorite drinks. And let's not forget the role of solubility changes. They can affect the performance of a product due to changes in particle size, polymorphic form, and temperature. Subscribe for more because you won't find me later. Keep exploring, keep learning.